Hello, so I found this guy who does statistics videos, which I'm going to use probably for myself in my statistics class. I like him. It's Statistics. So he's got one that says teach me statistics in half an hour. I'm probably going to play. But he also has like regression. He has them all broken down into smaller things too, which I might use to help get my homework done. So I'm actually going to subscribe because I might need him. Distribution, statistical inference, hypothesis testing. Yeah, definitely gonna need him. So, but I'm gonna play this video. So it says in 30 minutes, in half an hour, but it's a 42-minute video, so.
But Justin Zeltzer here from zstatistics.com, where today I'm responding to a challenge that was issued to me. Someone asked me if I could explain statistics to them in under half an hour. And while initially I thought that was a bit of an ambitious ask, I thought, no, that's actually a really good challenge. And one that I thought I might do for everybody. So this is it, an introduction to statistics, with no maths, and done in under half an hour. Now you can probably see that the timing of this video is a bit longer than that, but it is because I bunged on a little extra section at the end, which is a bit of an optional extra. But I think I get most of it done in under half an hour. But the idea is for you to develop your intuition around statistics. So it's great for those people who are just enrolling in a statistics course and are a bit apprehensive, or for others who aren't studying statistics but kind of want to know what it's all about. And to keep it light and interesting, I've themed all of the examples in this video on my latest obsession, which is the NBA. Despite proudly following Australian sports, my brother's getting me hopelessly addicted to American basketball. So here we go. The first thing we're going to delve into is what types of data we're going to encounter when we're dealing with statistics. Now, roughly we can divide data into two distinct classes: categorical data and numerical data. Now, these sound somewhat self-explanatory because they are. Numerical means numbers and categorical means categories. So I'll give you some examples of those in a second. But categorical data can be further split into nominal categorical data and ordinal categorical data. Nominal meaning there is no order to the various categories of a particular variable. And ordinal means that there is some kind of order to the categories, and we'll see some examples in a sec. Numerical data can be further split into discrete numerical data or continuous numerical data. And again, we'll have a look at some examples right now, actually. So if I was to ask you, what team does Stephen Curry play for? You can see that clearly the answer to that question is not going to be numerical. So it's a categorical piece of data. And here in these brackets, I've put what's called the sample space for this particular question. Now, Steph Curry could either play for the Atlanta Hawks, the Boston Celtics, etc., etc. Turns out he plays for the Golden State Warriors, but all these potential values for what team Steph Curry plays for, when we combine them, we call that the sample space. And you can see that there's no order to the teams. It doesn't really matter which order you put them in. So that's why we would say this is a nominal piece of data. Now the question, what position does Steph play? Well, that might provide us with ordinal categorical data. Now Steph could either play guard, forward, or center, or you could split that up into point guard, shooting guard, etc., etc. But there is some loose order to these positions. The guards generally play in the backcourt, and then the forwards play closer to the ring, and the center plays underneath it. And also there's the general kind of height difference between smaller players that play guard to taller players playing forward, and the tallest will play at center. So while this is still categorical data, there's some kind of order to it. Now, an example of discrete numerical data might be how many free throws has Steph missed tonight? Clearly, he can miss 0, 1, 2, 3, etc., etc. This is numerical data, but importantly, he can't miss 1.5 or 2.3 free throws, right? So there are only discrete possible values that this piece of data can take. And finally, continuous data might be the question, what's Steph's height? Now, Google lists Steph's height as 191 centimeters, but of course, Steph's actual height might be something like 191.3217. You can keep subdividing these centimeters into as many decimal places as you like. So height in this instance is an example of a continuous numerical piece of data. Generally, we kind of make height a discrete piece of data because we only really are interested in whole centimeters, or in the case of the imperial measure, whole inches. We don't usually care if someone's, 6'3.5" or 6'3 2/3, but in a pure sense, you could say that height is continuous. Now, here's an interesting question. If I asked you what is Steph's three-point percentage this season, what kind of data do you think that is? Is it categorical? Is it numerical? And which of these subcategories would this relate to? Maybe you want to pause the video and have a think. But spoiler alert, I'm going to tell you right now. When we have a quick look at what proportions, in fact, are. Now, just appreciate that percentages and proportions are pretty much the same thing. One's just expressed in terms of being out of 100, and the other one is just a number between 0 and 1. But it's the same thing. Alright. Now, if I was to ask you, what is Steph's three-point percentage this season, what type of data do you think this is? Is it categorical or is it numerical? And which subcategory do you think it fits into? Well, feel free to pause the video and have a think about it, but spoiler alert, I'm about to ruin it for you when we have a look at a special kind of data called proportions. Now, even though I've asked for Steph's three-point percentage, hopefully you can appreciate that a percentage is in fact just a proportion that's being expressed out of 100. But we'll note that each three-point attempt that Steph makes actually provides us with nominal data. So it's either a three-point that's made or a three-point that's missed. So what a proportion does is that it aggregates this information to provide a numerical summary figure. So in some senses, a proportion is numerical because obviously it provides us with a number, but it's built up of nominal data. Now, Steph Curry, in this season so far, in 2018-19, has made 128 three-point shots, and this is his percentage, 0.4766. So each of these 128 shots are actually nominal pieces of information. And this proportion is some kind of summary of that. Here's an interesting question for you. Is a proportion discrete or continuous numerical data? Now, that's not necessarily so obvious a question, and I might leave that to you to answer in the comments of this video, so feel free to start a little discussion on that. It's an interesting one, I think. Anyway, that's your data types. Now, distributions. If I was to ask how are the heights of NBA players distributed? Now, the smallest player currently playing in the 2018-19 season is Isaiah Thomas at 5'9", and the largest player is Boban Marjanovic at 7'3". Now, all the other players will fit somewhere between the smallest and largest. Here we go, there's a picky of both of those two players. Anyway, what we can present is something called a probability density function, which essentially describes the distribution of all the players in between the smallest and largest player here. So you can think about it in two ways. It's either the distribution of the whole population of basketball players that we have in the NBA, Or alternatively, it's the probability of selecting someone at random from that population at every given height. So quite clearly, as the bulk of the players are going to be somewhere in the middle, say 6'6" or 6'5" or something, if I was to select someone at random, I would have the highest probability of selecting someone around that height, as opposed to selecting someone at 5'9" or 7'3". There's just less players at those heights, right? Now this curve I'm presenting here is a very common curve in statistics. Some people call it a bell curve, other people call it a normal distribution, but it's a very commonly occurring distribution in statistics. And it basically just means that the bulk of the distribution happens towards the middle, and it gets rarer as you go towards the extremes. Now I've created a whole video on the normal distribution, which I'll put a little flash hyperlink up now for if you're keen on learning a bit more about it. But there's a symmetry about this distribution, with the bulk of the players being around that height. Now I've just assumed that this would be the distribution of basketballers' heights, but what other possible distributions might there be? A distribution like this would indicate that it's the same probability that if I was to select someone at random from the NBA, there'd be the same probability of being 6'6" as they would of being 5'9", or indeed 7'3". This is called a uniform distribution, which probably doesn't match up with the reality of the NBA. A distribution like this, we can call this a bimodal distribution. It's got two modes, where the mode is just the highest peak of the graph. Or something like this, which is a skewed distribution. Let's just say that there's a larger predominance of players up towards the 7-foot mark, and it gets a lot more scarce down towards these smaller players. And this particular type of skew is actually called left skew because the tail points in the left direction. You can guess what right skew might look like. Now, before we move on to have a look at sampling distributions, I just want to reiterate that this distribution we've been looking at describes the probability distribution of heights if I was to select one single player. But what if I had a whole sample of players, say 10 players, and I wanted to know what is the distribution, what is the probability distribution of their average height? Well, for that, we'll be looking at sampling distributions. So the question is, if I select 10 players at random, what is the probability distribution of their average height? Okay, well, here's the underlying distribution again. Now there's 5'9", and there's 7'3", and if I was to select someone at random, their probability density function would be a bit like that. But if I select 10 people and take a look at their average, what will that distribution look like? And it turns out that it'll have the same mean, but it'll be a lot skinnier. Now, why is that? Well, think of it this way. If I select someone at random, it's possible that I select Isaiah Thomas. He's 5'9", and while there might only be a few of him in the league that are that small, it's still possible that I select that player at random. But if I'm selecting 10 players, the probability of them having an average height of 5'9" is very, very, very small indeed. Eventually, after selecting Isaiah Thomas maybe, I'll have to select other players, and it's likely that they're going to be somewhere else in the distribution so that their average gets shifted up, right? When you take a sample, the larger your sample size is, the more unlikely you are to get extreme sample means. So that's why this distribution is going to be a lot skinnier than the distribution on the left here. And this is important in statistics because every study that ever gets conducted starts with a sample. You want to test some kind of effect. So you take a sample and then you make an inference using that sample. So it's important for us to get a handle on what happens when we take a sample. The distribution becomes a lot skinnier, or in other words, the variance of our statistic is reduced. And that indeed takes us to sampling and estimation. My question is, how good is Steph Curry currently at three-pointers? So in the current season, 2018-19, he's shot 128 threes and has nailed 61 of them, so that's .4766. What I'm going to try to get across here is that this is actually a sample statistic. He has a sample of size 128. He has 128 three-point attempts, and 61 of them have been successes. So here we have that proportion, .4766, which is our sample statistic. Now when I ask you how good is Steph Curry at three-pointers, appreciate that this .4766 is actually an estimate for this thing we're going to call theta. Now theta is a Greek letter, and it represents exactly how good Steph Curry is. It's something we can never know. Maybe he's a 50% shooter, but this season he's just a little bit off. Or maybe he only shoots at 42%, and this season he's doing much better. But either way, what statistics does is it creates this unknowable, almost godlike value of theta, which we can then try to estimate by taking a sample. So given our sample, where Steph Curry has currently got .4766, maybe the best estimate for theta might be .4766. As in, if you were trying to guess what you think Steph Curry's long-run three-point percentage would be, .4766 is probably your best bet. But appreciate that there's some kind of variance around this estimate, some kind of uncertainty. If Steph Curry shoots some more three-pointers, this proportion could either go up or down, right? And all of a sudden, that would be our new best estimate for theta. The whole idea behind statistics is trying to get a hold of the uncertainty you have behind your estimates. Now, I'm not going to enter into calculations of these particular intervals in this video, but I've made plenty of videos that delve into this precise question. But what statisticians like to do is create these things called 95% confidence intervals, where we can say, look, we don't know what theta is, but given our sample, we have a 95% confidence that theta is between these two particular values. And generally, our sample estimate is bang in the middle of those two limits. So that's what you're going to be doing when you study statistics. You're going to be developing means of calculating, of quantifying this uncertainty you have over Steph Curry's long-term three-point percentage, or other things maybe more meaningful. Now here's an interesting point. We all know that Steph Curry is probably the best three-point shooter in the league, if not in basketball history. But at this point in the 2018-2019 season, we're only about sort of 12 or 13 games in at this point. There's a player called Myers Leonard who scored 9 out of 15 three-pointers and has a three-point percentage of .6. Now, who do you think out of these two players is the better three-point shooter? If you were just looking at the sample statistics here, you'd say, well, Myers Leonard is, right? Because he's got a 60% or .6 proportion for three-pointers, whereas Steph Curry's only shooting .476. So what is it about Myers Leonard that might tweak your intuition that something's not quite right here? Well, let's investigate in a statistical way. This .6 that we've got for Myers Leonard is an estimate for his theta, and I've got this in green now. This is a different theta to the one we saw before, which was for Steph Curry. But this is Myers Leonard's long-term three-point percentage. And the best estimate for that, again, is our sample estimate, which is .6000. But in this case, we might find that the confidence interval we create is a lot larger for Myers Leonard than it is for Steph Curry. Why is it a lot larger for Myers Leonard? Well, because he's only had 15 three-point attempts in the season so far. So we're going to be less sure about where this value of theta is going to be for Myers Leonard. But again, we can construct his 95% confidence interval, which is going to be a lot wider than Steph Curry's, because we actually had more information for Steph Curry. So if you put both of these two side by side, the red being Steph Curry and the green being Myers Leonard, it's true that if we didn't know anything about these two players, we'd still have the best estimate for Myers-Leonard being higher than for Steph Curry. But you can see we'd have a much larger confidence interval for Myers-Leonard. In other words, we'd be less confident about where his long-term three-point percentage is going to be. And it could be down here below Steph Curry's. And knowing what we do about the two players, it's probably likely to be less than Steph Curry's. So again, this is preparing you for what statistics can do, which is deal and quantify uncertainty. Now we've met theta just a second ago, which is this long-term three-point percentage. But when I described it as a Greek letter, I was referring to it essentially as what we call a parameter. Now let's have a look at some common parameters that we're going to see in the study of statistics. You might have heard of some of these. Mu is often used for the mean of a numerical variable. So for example, the mean height of players might be given mu. Sigma is the standard deviation of a numerical variable. Now I haven't dealt with standard deviation in this video, but all standard deviation is a measure of the variation, a measure of the uncertainty of a particular estimate, or the variation of a particular distribution. Another parameter, pi, these are all Greek letters by the way, if you haven't noticed. Pi is for the proportion of a categorical variable, so I could have used pi in that example I just gave. I ended up using theta, and as I say down the bottom here, theta is generally used for all parameters in some texts. And I like using theta because it sort of is a bit more general, but pi is sometimes used for the proportion. Rho is used when you're dealing with the correlation between two variables, and beta is used for the gradient between two variables, and that's often used in regression, which is a very important topic in statistics, and one for which I've put together a whole series of videos. So you can investigate the videos I've done on regression if you like. Now again, all these represent parameters, or those unknowable fixed values that we try to estimate. Now they themselves do not have any uncertainty about them, technically. They are these godly figures that we just try to merely estimate as mere statisticians. And the way we estimate them is by taking a sample, and those sample statistics are given other symbols. For a numerical variable, say height, if we're taking the average height of a sample, that gets given the symbol x bar. A standard deviation is given the symbol s. P is generally used for proportion, R for correlation, and B for the gradient. So be prepared to see all of these particular lowercase Roman numerals to represent the sample values that estimate these parameters provided in Greek. But I will say, be prepared also for your statistics textbook to break all of those rules, because despite them being conventions, sometimes you'll find they don't stick to them, annoyingly. Alright, so with that under our belt, let's go and have a look at a very common topic in statistics called hypothesis testing. Now I'm going to start you off with an example rather than give you some kind of hypothetical definition here. But using the data we've just seen, is there enough evidence to suggest that Myers-Leonard is shooting above 50%? So let's review his stats again. He's got 9 3-pointers made out of 15, and that's 0.6. So yeah, sure, his sample is greater than 50%, 0.5, but is that suggesting to us that his long-term 3-point performance is going to be above 0.5? Well, that is a question worthy of a hypothesis test. So as we saw in the previous section, there's going to be some variation or variance around this estimate 0.600. It's not as if that's going to definitely be his long-term 3-point proportion. So what statisticians like to do is they like to set this thing called a null hypothesis. And it's given the expression H0. And here we're going to set the null hypothesis to be that Myers-Leonard's long-term 3-point percentage is less than or equal to 50%, less than or equal to 0.5. Now, why might we do that? Well, as a statistician, we're always very conservative. We assume that the reverse is true, and then see if there's enough evidence to really budge from that assumption. It's kind of like when someone's on trial. The null hypothesis might be that they're innocent, and you really need a lot of evidence to budge from that null hypothesis. It's not good enough that there's just a little bit of evidence. You really need evidence beyond reasonable doubt, right? And that's the same with hypothesis tests. So this here on the right-hand side is called the alternate hypothesis. And in general, whenever we're doing a hypothesis test in statistics, whatever we're seeking evidence for goes in the alternate hypothesis. Just for the reason that we're very conservative as statisticians. We're always going to have a null hypothesis, that the reverse is in fact true, and we're going to see if our sample is extreme enough, is far enough away from that null hypothesis to suggest that the alternate hypothesis might be true. This is the way you're going to be framing your thinking when you're dealing with statistics. Now, one thing that different textbooks will do will have different ways of describing a null hypothesis. They both mean the same thing, but some will say theta is less than or equal to 0.5, and others might say something like theta is equal to 0.5, and it doesn't much matter, because the important thing is that theta being greater than 0.5 is in our alternate hypothesis. So let's see how this pans out using what we understand now from a probability distribution. So essentially what we're going to do is we're going to start with this null hypothesis that theta is equal to 0.5. And if it indeed is equal to 0.5, how many three-pointers out of 15 would Myers-Leonard sink? Well, here's the probability distribution. If he truly is a 50% three-point shooter, an exactly 50% three-point shooter, if he shoots 15 three-pointers, on average he's going to get 7.5 of those in, right? But of course you can't sink exactly 7.5, so 7 and 8, they'll be approximately the same height, so they'll have the same probability of occurring. He's less likely to get 6 and 9, less likely again to get 5 and 10, etc., etc., etc. So this is the probability distribution of Myers-Leonard's 15 three-point attempts, where the number of successes are on this axis, assuming the null hypothesis is true. Now, for those advanced players, this is actually a binomial distribution. If you're keen on learning more, I'll put a link up here. Now, what did he get in this sample? Well, he actually got 9. So what this tells us is that if indeed he has a 50% three-point percentage, it's still quite likely for him to get 9 three-pointers out of 15. It's not beyond the realm of possibility that he could be a 50% three-point shooter and just happen to do a little bit better in his first 15 shots than expected. Now, if I was to ask you how much doubt this sample is casting on our null hypothesis, in this case you'd say, well, not very much. What if I then told you that, say, someone else scored 12 out of 15 three-pointers? Or let's just say Myers scored 12 out of 15 instead. At that point, you're starting to think, you know what? That's quite unlikely now. It's still possible that he's truly a 50% three-point shooter and managed to just do better in his first 15 than we expected. But it's starting to now cast some doubt on our null hypothesis. And this is what a hypothesis test does. It takes the sample and says, how extreme is that sample? Is it too extreme, given our null hypothesis, for us to realistically hold on to that null hypothesis? So in reality, what's going to happen is we're going to construct what's called a rejection region. We'll find a point on this x-axis here, beyond which we're going to consider it too extreme to realistically hold on to the null hypothesis being true. Now, this yellow area can effectively be customized to determine how strict you want to be with rejecting this null hypothesis, but often it's chosen as 5% of the entire distribution. And we call this the level of significance. So we might say that the level of significance here is 5% because if our sample statistic is in this upper 5%, we will consider it too extreme for the null hypothesis, and therefore reject the null hypothesis. So, just to repeat, in this case, because Myers-Leonard got 9 out of 15, or 0.6, he was, in this point here, he was at 9, therefore not extreme enough to reject the null hypothesis. So even though in the sample he was shooting above 50%, it wasn't extreme enough to allow us to infer that he's shooting 50% in the long term. We need more evidence as conservative statisticians. Anyway, so I just got a little extra section here for hypothesis testing, just for you to be aware of two important notes. The first thing is that we never ever prove anything in a hypothesis test. So here again is that setup with Myers-Leonard and our conclusion, which was to not reject the null hypothesis, as in there's not enough evidence to suggest Myers-Leonard is shooting above 50%. Never say the word prove in your conclusion, which is the frustrating thing about statistics, I guess. You can never prove anything at all. All you can do is infer. So we were unable to infer that Myers-Leonard is shooting above 50%. The other thing we never say is the word accept. So notice I've written do not reject the null hypothesis. So this was our null, but in the event that we do not reject it, you should never say the word we then accept the null hypothesis. Because don't forget, he scored 60% out of the first 15 three-pointers. So it's not as if we have evidence that he's less than a 50% three-point shooter. It's just that we don't have evidence that he's more than a 50% three-point shooter. And that's a really important distinction. In fact, our whole judicial system relies on that distinction. When you find someone not guilty, that doesn't necessarily mean that they're innocent, right? It just means that there's not been enough evidence to convince you of their guilt. And because of the presumption of innocence, they walk free. Okay, so let's have a look at p-values now. They're the much maligned p-values in statistics. Now, to introduce them, I've said considering a null hypothesis, so whatever null hypothesis we're testing, hypothesis tests assess if our sample is extreme enough to reject the null hypothesis. That's exactly what we did in the last section. What the p-value does is it then measures how extreme the sample is. So the hypothesis tests sort of set up the goalposts and we assess whether we've scored the goal or not. But the p-value measures out exactly how far we kicked the ball, to continue with a fairly loose analogy there. So here's the example again. We're using the same setup as before with Myers-Leonard's 50% three-point percentage. So our test statistic was 9, so he got 9 out of 15 three-pointers, right? And this is the distribution under the null hypothesis. So how extreme was his test statistic that we got? Well, we found out it wasn't extreme enough, right? So the hypothesis test said, reject the null hypothesis if the test statistic is in the top 5% of the distribution. And indeed, we found that he was not in the top 5% of the distribution. What the p-value does is it takes our test statistic and actually calculates that region. So it says our test statistic is in the top 30.4% of the distribution, 0.304. So it's actually measuring how much of the distribution is at or above our test statistic. So in other words, it's measuring how extreme our sample is. So if our p-value is very small, the more extreme our sample must have been, and therefore the more likely we are to reject the null hypothesis. And if the p-value is large, we're less likely to reject the null hypothesis. So if it's closer to 1, as this one is, this was 0.3, so we had quite a large pink area here, we become less likely to reject the null hypothesis. And that's exactly what happened in our case. We did not reject the null hypothesis. Now, the final point I might make, and it's something that you probably have figured out already maybe, But if this p-value drops below 0.05, it implies that our test statistic must be in the rejection region. Let me repeat that. If the p-value is less than 0.05, it means that our test statistic, wherever we are, must be in the rejection region. So that rejection region was constructed, that yellow bit, let's go back. That yellow bit was constructed so there's 5% that's been highlighted. 5% of the whole distribution that's been highlighted. So if our p-value is less than 5% or less than 0.05, if the pink bit was less than 0.05, we know that we must be somewhere in that rejection region. Our test statistic must be in the rejection region. So what that implies is that if the p-value is less than the level of significance for your hypothesis test, you're going to reject the null hypothesis. So it's a really quick way of assessing whether we're going to be rejecting our null hypothesis. Right? So all up, whenever you conduct a hypothesis test, let's sort of recap. Whatever you're seeking evidence for goes in your alternate hypothesis. And then if you conduct the test and your p-value is very, very small, that provides evidence for that alternate hypothesis. It provides evidence enough for us to reject the null hypothesis. Alright, so that's pretty much it for the theoretical component of this video. Stop the clock. Did I get under 30 minutes? I don't think so. I think it was a few minutes over. But I'm not even going to quite stop the video here because I figured I might give you an extra little section to do with p-values because they've been in the news over the last few years, I would say, and not necessarily in a good way. People have been throwing a lot of shade at scientific research over the last little while, and it's somewhat justified due to this thing called p-hacking. So if you've had enough with the theoretical component of the stats today, well, I'll tell you that's it, we're done. But let's have a look at p-hacking to see how a misuse of p-values can invalidate scientific research. So let's talk about what p-hacking's all about, and I might start with that same boring old probability density function that we saw before. Now, as we've seen in hypothesis testing, we start with the null hypothesis that there's no effect. And then we take a sample, and we want to see a sample that's extreme enough for us to reject that null hypothesis. So we'll construct this rejection region, which is this yellow shaded region up here. My choice of colours might not have been the best, but hopefully you can see that's shaded yellow. And so if our sample lies up in this region here, we're able to reject the null hypothesis. And in doing so, we would say that there's a significant effect. And all of a sudden, that's great. We'll be able to publish our paper to show that X affects Y, and we'll get all the plaudits from the research community. But here's the thing. Remember how I said that statistics doesn't prove anything? Well, this is exactly the case. If we have a sample which is in our rejection region, in other words, a sample which is extreme enough for us to reject the null hypothesis, it doesn't mean the null hypothesis is false. It's still possible that we just happen to get a freak sample, right? The whole purpose of a p-value is to say, well, how likely is it for us to get this sample statistic if the null hypothesis is true? And if the p-value is low enough, we go, oh, that's starting to become too low. But at the same time, as long as that p-value is non-zero, there is an outside chance that you just happen to get a freak sample where there was in fact no effect. To put it in basketball terms, just say Myers Leonard was a 50% three-point shooter. It's still possible for him to score 14 or 15 out of 15 three-pointers, right? Very unlikely if his true three-point percentage was 50%. But it's possible. So how does this relate to good and bad research? Well, in good research, what you do is you theorize some kind of effect, and maybe that might be that red wine causes cancer. Let's just say that as our example, right? We then collect our data, and we test only that effect, red wine causing cancer. And if we find the p-value of this test less than 0.05, we can conclude some strong evidence for the effect of red wine on cancer. And that's all well and good, and that's good research. That process of theorizing some effect, then collecting your data and testing that exact effect is how one conducts good research. Now, bad research gets conducted like this, and unfortunately, I'm going to suggest this gets done all the time. If you collect your data first with just the general idea of let's see what causes cancer. So let's collect a whole bunch of data from people that have cancer, a lot of lifestyle kinds of pieces of data as well, whether they smoke, whether they drink wine, all this kind of stuff. We're going to test all these different effects. We're going to test red wine. We're going to test smoking. We're going to test exercise. We're going to test exposure to main roads, all this kind of stuff. And then we're going to look through all those effects and find the ones where P is less than 0.05. And let's just say it happened to be for where we're testing red wine on cancer. And then we're going to publish our results and say, yep, red wine causes cancer because the p-value is less than 0.5. This is called p-hacking and is potentially rife in research, and it's quite problematic. Now, it's not necessarily obvious why this is so much worse than our good research over here on the left. But as I said before, when we conclude strong evidence for some effect, we're essentially saying there's a very, very low probability that this came about by chance. Now, what happens when you test 10 different things? If you test 10 different things, it becomes more likely that one of them, by chance, will be quite extreme in their sampling. Well, let's push it even further. If you test 20 different things, we're actually expecting one out of those 20 things to have a p-value less than 0.05. That's actually what the p-value means. If there's a 5% chance that the effect we've seen was just due to the randomness of the sampling process, then if we test 20 things, 5% of 20 is 1, one of those 20 things is likely to show that strength of effect. So that's where p-hacking comes into it. We test all these different things and we just find the one that happens to look significant, and we can then sort of pretend that that was the thing that we were looking for the whole time. And it's actually a big, big problem. Anyway, that's hopefully brought it into practice, some of the stuff that you can learn in statistics. And of course I've dealt with things in a very superficial way, but that was the whole point of this video. But look, if you like this, I've got more in-depth discussions, one where I go into the actual formula and the mathematics of it all. You can check it all out on zstatistics.com. But hey, if you dig it, you can like and subscribe and do all those things that you're meant to do. But yeah, hope you enjoyed.